Good morning, everybody. Just giving it a couple more minutes to see latecomers coming in, and then we'll start. My name's Mike Weaver, Associate Director for Sigma-HSE, based in Winchester, UK. And today we're going to talk about electrostatics. As you can see by the title, mitigating and eliminating electrostatic hazards. Right, I think we can start now, and anyone else will have to catch up. Right, the webinar objectives. On completion of the webinar, you will learn how static charge can be generated and accumulated in a manufacturing facility, the different types of electrostatic discharge and their relevance to the hazards that electrostatic poses, the different ways to control electrostatic charge generation, the accumulation of that charge, and how ignition can occur in order to reduce the risk. A little bit about Sigma. We have offices in Winchester, UK, New Delhi in India, Mumbai in India, Hyderabad in India, New Brunswick in New Jersey. Laboratories, we have a process safety lab in Winchester that can deal with electrostatics hazards testing. It can deal with dust and gas and vapor explosion testing, and can deal with chemical reaction hazards. And we have a process safety lab based in Delhi in India, about to move to Hyderabad by the end of September, and that does process safety testing for dusts. Our areas of expertise bring together our Indian and UK experts to provide our clients with EHS services, and hopefully we can help you with appropriate engineering solutions. We undertake laboratory testing in our UK laboratories following ISO, BSI and ASTM standards, and we cover consultancy, testing and training. Our consultancy team provides a wide range of specialist knowledge covering some of these are the following sectors: process safety management, its implementation and the review of your current documents; DSIR, dangerous substances, explosive atmospheres regulations; and ATEX, atmosphere explosive assessments. We can do hazard identification or hazard operational surveys and sit on the teams and lead or scribe. Process hazard analysis, functional safety, things like LOPA, seal determinations, chemical reaction hazards, and training workshops. These can be in-house or can be public ones, or as you're doing today, a webinar. Laboratory testing, as I explained shortly, was powder, fire and explosion properties. That's all the different dust tests to look at fire and explosion properties. Gas and vapor properties, including things like flash point, LEL, AIT, etc. Electrostatic properties, which are relevant to this talk. So we can do minimum ignition energy, powder volume resistivity, charge relaxation time, chargeability measurements, etc., liquid conductivity. And we can do chemical reaction hazards testing in our UK laboratory. So why are we talking about electrostatics? Well, it's one of 13 potential ignition sources given in the standard EN 1127. It's also specifically mentioned to be assessed in ATEX and DSIR, and is the only ignition source specifically picked out. It's not well understood. People misinterpret it, try to do things which they believe to be right, and quite often can end up making the situation worse. Too complicated, a dark art, often blamed as an ignition source when sometimes it's not. Sometimes people don't believe that electrostatic problems exist. One plant I went on, for instance, I mentioned about powder transfer and the risk of sparks. They told me they'd never seen one before. I was stood there with the EHS manager watching a charging process, and the EHS manager got very excited and pulled me out in the corridor and asked me if I'd seen the spark. I said no, I was stood round the other side. He said the spark was 4 inches long and scared him. And I'd actually mentioned this can happen. I didn't see it, the operator didn't see it, but he was in the right position to see it. So sometimes when you don't see ignition sources, you're just not in the right place. It's ever present. It's inherent in majority of processes, and it's caused quite a few industrial accidents. A few of them to look at: Barton solvents explosion, flammable liquid storage tank farm explosion, static discharge ignited ethyl acetate vapors. The complete tank farm was destroyed. Nearby communities were evacuated, with large pieces of the plant landing on nearby buildings. The spark was caused because they had an isolated conductor they hadn't identified. ExxonMobil explosion. Electrostatic precipitator, hydrocarbon, entered the ESP and exploded because of the continuous spark availability. There was on-site property damage and there was injury reported to about operators. Caswell adhesives, ignition of flammable vapors due to a static discharge. The fire destroyed the building. More than 60 firefighters were required to tackle the flames. 35 firefighters and 2 people were treated in hospital after breathing chemical fumes and smoke. The published guidelines that we work to are BSEN 60079-32-1 from 2015. Explosive Atmospheres Electrostatic Hazards Guidelines. This is basically the Bible for the European community. And in America, we have NFPA 77, 2014, the recommended practice on static electricity. So, ignition sources by type of equipment. You can see here a graph, and it shows ignition by static, mechanical, and smoldering. Mechanical is the biggest ignition source by far of anything. But if you look here, lots of the operations that happen, electrostatic discharges can be the source of ignition. From silos and bunkers, dust collectors, mills, size reduction, conveying of materials, especially insulating products, dryers, mixers. You can see a high proportion of potential ignition sources are electrostatic in mixers. In H, we have sieving. So you can see it covers a wide band of equipment types where you can possibly get an electrostatic discharge. Understanding static electricity. Firstly, remember, static electricity is generated wherever movement takes place. You get a shock. Why? If you look at the pictures above, you'll see a man walking towards a door. While he's walking, movement is taking place. He has probably got insulating shoes. The carpet could be of a nylon structure. You find this yourself in shops where you've touched metal coat rails, the door handles, etc., and you've given a massive shock, and it hurts because during the movement you're getting electrostatic charge generation. And worse than that, you get in charge accumulation because you are insulated from earth. The moment you touch the door handle, a metal door handle for instance, then that is earthed and you discharge. That's why you get the shock. It's you discharging to the door, not the other way round. The same applies in a car. You're traveling in a car, your movement is generating electrostatic charge. Again, you're sitting on insulating carpets, you may have insulating shoes, and you become the same charge level as the car itself. Then you get out of the car. Plastic door cards, you push them. As you separate the charge, you could become positive or negative, and the car becomes the opposing charge. The car has anti-static wheels, tires. Millions of pounds are spent by tire manufacturers to make them static dissipative, so the car loses its charge rapidly. On the other hand, you're stood on insulating shoes, you go to close the door, you touch the metal, and bang, you give the car a discharge up to about 25 to 30 millijoules, and it hurts. It's you discharging to the car again. So, static electricity is defined as an imbalance. This is a surplus or a deficit of electric charge within or on the surface of a material. So there's two ways you can discharge. You can discharge surface-wise or volume-wise through the material or across the surface. This can happen on floors, for instance, where you need to measure along the surface and through the material. The phenomenon of static electricity requires separation of positive and negative charges. As per the example in the car, separation occurs once you leave the car. Static electricity is very similar or the same as mains electricity. It obeys the same rules, but static electricity is generated in a different way. Mains electricity is a constant voltage system. So you may have a 230, 240 volt system, a 110 volt system, a 220 volt system. But static electricity is a constant current system, which is different. The voltages will change. So the uses of static electricity can be very useful in photocopiers, static dissipatators. Spraying is very useful, applying electrostatic charge. And then you've got printers, they use electrostatic charge. Powder coating, for instance, uses electrostatic charge to coat metal and give an even coating of paint. As well as being useful, problems caused by electrostatic include shocks, nuisance. You know yourself, everybody, I believe, has experienced an electrostatic shock. It's very uncomfortable and it's nuisance. You don't like it and you want to get rid of it. The other thing it can do is make you jump backwards. So if you're on an upper gantry and you get a big enough shock, it could actually throw you over the railings where you jump back so fast. And some of the shocks can be extremely painful. If you have propagating brush discharge shock, for instance, it can even knock you out unconscious. Clinging powder attraction. You know yourself, if you look when you're manufacturing, you can look inside vessels and you see powder clinging to the sides. This is caused by static electricity, and the two are clinging together, and often they take quite a bit to get them apart. The opposite is powder segregation, separation of the particles. And this can be extremely difficult in industry, especially in the pharmaceutical industry, where you've got very small micrograms of active pharmaceutical ingredient that you want to stay mixed with the excipients. And yet, if you've got the wrong type of powder, you can get powder segregation and separation of the products. The worst case scenario would be electrostatic discharges in an EX rated area. In other words, a hazardous area. This is your worst case scenario because now you have the possibility for fires, you have the possibility for explosion. That's why it's very important to ensure you get an electrostatic assessment done of your plant if you believe there is a problem with electrostatic charge generation and accumulation and then potential discharge. So here again, a picture of a worst case scenario. A flammable atmosphere, flammable liquid by looks like in this case, electrostatic discharge, large fire, explosion and smoke. This is avoidable if you know what you're doing with electrostatics and you can make sure that you're safe. We have a few definitions with electrostatics, and you need to know these before you can do an electrostatic assessment. Conductive. This has got a low electrical resistance. Electrons flow easily across the surface or through the bulk of these materials. Typical conductors are stainless steel, mild steel, copper, brass, the metals. Some carbons, if they're in carbon fiber, for instance, could present a problem. The charges go to ground or to another conductive object that the material contacts or comes close to. This is good in some ways, that you get a discharge through the objects without causing a spark if they're joined together. On the other hand, if they contact one another and are separated and they come together, they could generate a spark. They possess a conductivity greater than 10 to the 4 picosiemens per meter. Antistatic, static dissipative, the ones you hear people talking about. These are materials which are between conductive and insulating. For instance, if you're talking about personnel, you don't really want them on conductive materials because if they do discharge, it could be violent and could cause injuries. Therefore, quite often anti-static, static dissipative mats are used, which discharge the charge generation on personnel more slowly, more controlled. The charges flow to ground more slowly in an anti-static material and in a somewhat more controlled manner than with conductive materials. Charge generation rate is less than charge relaxation rate. In other words, it releases its charge faster than it builds it up, and therefore you end up with a safe condition. Non-conductive. Non-conductive. These materials prevent or limit the flow of electrons across their surface or through their volume. They're insulators. They have a high electrical resistance and are difficult to ground. You cannot ground insulating material because the electrons will not flow to Earth through it because of its insulating nature. The static charges remain in place on these materials for a very long time. We had an active pharmaceutical that we left in an earthed vessel for 28 days, and it didn't lose 1 unit of charge in that time period. That goes to show earthing of a very strong insulator is not the effective way to deal with it. Charge generation rate is greater than charge relaxation rate. In other words, it builds up charge faster than it can lose it. Static electric discharge. This is the release of static electricity in the form of either a spark, a brush discharge, the most powerful propagating brush discharge, a cone discharge, often found in silos or vessels, or a corona discharge, often off a point or a leading edge material, such as a conductor, that might be capable of causing ignition under appropriate circumstances. So static hazard assessments. As you can see, it involves several items you need to consider. Do you get charge generation within your process or on people? Can that charge accumulate? Importantly, can this happen within a flammable atmosphere, an EX or hazardous area? Do you know the material ignition sensitivity? Is it very low, 3 millijoules, or high, greater than 500 millijoules? What type of discharge can you get? Can you get a brush discharge, propagating brush discharge, or a spark discharge, for instance? If you look at this diagram, you'll see some of the properties you need to consider. Obviously, you need to understand the hazardous area classification. Have you got a zone 0, a zone 1, or zone 2 in this tank? Do you know the flash point of the material? Are you working above the flash point of the material? Do you know the limiting oxygen concentration of the product? Is it low, 5%, or much higher, say 15%? Is the liquid conductive or insulating? In what gas group are you falling into it? A 2A, 2B, or 2C? Do you know the minimum ignition energy of the product? Most flammable liquids tend to be less than 1 millijoule. So we often look at flammable liquids and assume that is going to be the worst case. Acetone is slightly above that at about 2 millijoules. Do you know the vapor density? Does the product rise, in which case you've got a problem in the head, or does it fall, in which case you've got a problem at floor level? And do you know the flammable concentration, the LEL, UEL, lower explosion limit and upper explosion limit? The same applies for dusts. Again, the hazardous area classification you need to look at. Have you got a zone 20, 21, or 22? Do you know the minimum ignition energy of the dust? These can vary considerably, from less than 3 millijoules, like a gas or a vapor, up to much larger ones of greater than 500 millijoules. The minimum explosive concentration, MEC, which is similar to the LEL for liquids. The powder resistivity, often called the powder volume resistivity. Is it a conducting material or an insulating material or a static dissipative material? How long does it take for the charge to relax? Do you know the limiting oxygen concentration? And for dust, this can vary from 4% up to 18% or more. And do you know the particle size of the product? If it's less than 500 micron, then you've got a potential fire and explosion problem. Now we'll have a look at charge generation now. Most common charging mechanisms, as you can see on the right, are contact or tribo-charging. So it depends where the material is on the triboelectric series. Is it towards the conducting end or the insulating end or in the middle, anti-static. You can see by pouring powder, liquid going through a pipe, someone walking, a roller over sheet material, spraying. You see the separating of charge on the mists and the gun itself. And then it could be filling a vessel, again with agitation, which could make it worse. At least one of the materials must be non-conducting, insulating. Other mechanisms are charge sharing and induction charging, which are only for conductors. So contact charging examples. Liquid transfer through hoses and pipes. Agitation of a two-phase mixture. I've witnessed discharges in glass reactor vessels where this has caused so much electrostatic charge it's actually blown through the glass, and very difficult to stop it doing it. Settling of two-phase mixtures. So as the materials separate, so they build up charge and it's shared between the two systems. Filtration systems, where you're filtrating, you have agitation and therefore you'll get charge accumulation. In powder handling, you get sieving, again, quite a violent thing. Pouring, you're pouring into a vessel. As you pour it in, the powder's charged. Mixing, as you mix, the blades cause, again, agitation. Milling, very active. Pneumatic transfer, again, one of the ones I've seen produce large amounts of charge. If we look at induction or ionic charging, you see we've got 4 diagrams there. Diagram 1, the 2 balls together. Diagram 2, they're still together. Diagram 3, the separation. And diagram 4, you can see they're completely separated, opposing charges. So 2 metal spheres are on insulating stands. The presence of a negative charge induces electrons to move from A to B. The 2-sphere system is polarized in diagram 2. Then you separate them. Sphere B is separated from sphere A using the insulating stand, and the 2 spheres have opposite charges. We have the positive and the negative. The excess charge distributes uniformly over the surface of the sphere. Bring these together, you could end up with a spark. Charge accumulation. This can occur from isolated metal plant, personnel, non-conducting insulating materials, bulk liquids, bulk powders, mists or dust clouds. Some instances here for conductors. We have an isolating pipe in the middle. The flanges are insulating it. As the material and product flows through, you generate charge. It remains on that piece of pipe, which makes it a dangerous piece of equipment because it could discharge if it gets near Earth. You've got a metal drum, normally very useful, but now stood on an insulating plastic, isolating it from floor. In C, you've got conducting material, normally very useful, but now it's in a plastic drum. So the charge remains on that conducting material. You've got someone walking with insulated shoes and the charge builds up on the person. And then you've got rings of insulating material on flanges. And these again can build up electrostatic charge. With insulators, you could use cling film, wrap going around your product. These are very insulating and can build up large amounts of charge. You could end up with an extract system, a filter system, or material flowing into a container. Again, all instances where large amounts of charge can accumulate. Now you need to know the 6 types of electrostatic discharges which can happen in an industrial plant. You get spark, brush, propagating brush, corona, and cone. Those are not listed in the order of energy. They're just listed to show you the different types, normally of frequency, that you get. Also outdoor, lightning types. Now lightning, you would deal with that with lightning conductor systems on your plant, so I'm not going to talk about that. But the effective and available energy depends on the source of the discharge. Spark discharge, a charged isolated conductor. Energy is a half times the capacitance times voltage squared. Can be up to 100, 150 millijoules. Some of the instances there are pouring into a drum and the wheels are nylon and insulated. So though you've got a metal drum, though you've got a metal trolley, if you're using the floor, you can't do it because the nylon wheels will stop the transference of the charge. You need to put a fly lead on. On this one, on B, you've got an isolated person. We've talked about that. You've got an insulating floor, possibly with insulating shoes, touches the door handle and gets a discharge. Isolated pipe section, insulating gaskets, bolts or sleeve connectors. And again, it's right next door to an earth pipe and it can discharge once the charge accumulates to a certain level. An isolated conducting liquid in an insulating plastic drum. Tip this into a metal reactor and it will discharge it to earth as it hits the earth metal reactor. Brush discharges. These are the ones you get when you take a nylon jumper off at night. You look down and you see tiny little discharges happening across the surface of the jumper and you hear the little crackling. This is the brush discharges. Energy, 3 to 4 millijoules. These will not ignite dust clouds, even though the MIE may be below 3 millijoule. If charges of one polarity are distributed on the surface of an insulator, brush discharges can occur as soon as the surface of an earthed electrode nears the surface. So, insulating plastic sacks, brush discharge from liquid surface of a charged insulating liquid. Charged dust clouds, charged thunderclouds. As the thunderclouds are massive, the energy is larger than 3 to 4 millijoules. So we have brush discharges now. Sorry. We have propagating brush discharges, the most violent of them all. High charging situations on high resistivity materials, insulator with metal close by. This is basically an electrolytic capacitor. Energy associated can be greater than 1 joule of energy. There's a high charging level on thin, highly insulating materials. So, for example, pneumatic conveying, you coat the inside of a metal pipe. And very thin layers of insulator can result in a propagating brush discharge. Internally coated cyclone, similar situation, insulating bulk container on earth discharge chute, and high-speed conveying belts. I think the worst one I saw these were very insulating thin plastic sheet thrown into a low waste bin, acetate sheet. A man came to push the sheets down and try to get more in as it was the weekend. Some of the sheets had stuck to the metal and he got a propagating brush discharge. The whole of his arm went black and he was in hospital for over 3 days. Corona discharges, occurrence highly charged conductor or insulator away from earth points, usually with a sharp point or edge. Energy, roughly less than 0.1 millijoules. Very sensitive gases could be ignited, or gas or oxygen mixtures. With cone discharges, these occur in normally silo situations, and these discharges are observed in connection with charged and highly insulating bulk solids fitted into silos and filled into silos and containers. Cone discharges aren't usually observed in volumes less than 1 cubic meter. You can see the luminous discharges, and they propagate along the surface of the cone. Up to 25 millijoules for fine powders, but this is where granular powders can create more of a problem. You get higher energies. These can get up to 100 odd millijoules of energy. They ignite vapors, gases, and sensitive dusts. I went to look at investigation in a silo, and a Japanese manufacturer of the silo had told them that a small piece of plastic inside the silo had caused the ignition. However, the material was very insulating, large granules with a fine dust cloud above it. After talking with operators and maintenance people, I find out that a maintenance guy observed absolute cone discharges, the fluorescent discharges, one night when he was maintaining the top of the silo, but he didn't report it. So obviously this was the case for the incident, and then they had to use nitrogen inerting to make it safe. Lightning type discharges. This is a massive electrostatic discharge between clouds or between a cloud and the Earth's surface. They occur in atmosphere with very large clouds, which are much, much bigger than industrial plant. So let's have a look at electrostatic hazards in the plant. Metal components. Isolated conducting fixed and mobile objects can store energy and be the source of spark discharges. Energies can be up in the range of 100, even up to 500 millijoules. Energy can be compared directly to the worst case MIE for the materials. In this case, a complete section of metal pipeline is isolated by the end fittings and nylon wheels. Personnel. The human body is a conductor and can be a source of spark energy. Charging by contact, by walking, sharing, and induction can occur. If you get a static shock, you'll soon know the level. About 0.1 millijoules, undetectable by touch, but can still ignite hydrogen and carbon disulfide in air and hydrocarbons in oxygen. 0.25 millijoules, still undetectable, but can ignite hydrocarbons or gases in air. 1 millijoule feels like a feather brushing against you, ignites some sensitive dust clouds. 10 millijoules gives you a prickling sensation and ignites quite a few dust clouds. 100 millijoules gives you slight muscular contraction, very incentive. And 1 joule, very sharp muscular contraction, can be extremely dangerous and basically incentive for everything and anything that's flammable. So charge generation of non-conductive solid materials, tribocharging, contact and separation with other surfaces, discrete or continuous, charge sharing, contact with other charged bodies or materials, ionic charging, but no charging by induction. Typical charging systems, movement of materials in plastic pipes, emptying and filling of plastic sacks and bags, processing sheet or film, sitting or walking on insulating materials. So non-conductive solid materials can isolate conductors. So this can happen when you've got nozzles and lances. Wire helices going through plastic pipes have to be earthed. Do not leave them on their own, otherwise they can build up static charge and discharge. Gaskets isolating the bottom of bins. Flanges isolating ball valves. Sometimes ball valves are set in PTFE. And again, you have to make sure the ball valve inside is insulated as well as the outside. Backing flanges. It lead to ignition risk. You can get brush discharge, ignite gases, vapors, but not dusts, propagating brush discharges, ignite gases, vapors, and most dusts. So powder charging, again, large amounts of movement, therefore insulated materials in particular, you expect to get large amounts of charge generation. This can occur when conveying powders, milling and grinding, sieving, pouring into vessels, filling, emptying vessels, sacks, etc. Need to measure the volume resistivity and charge relaxation time of the products to see if they can build up and hold electrostatic charge. Again, I attended an incident where they had flammable vapors poured in an insulating material and they had a discharge in the mouth of the vessel. So liquid charging. Charge is generated in liquids during pumping, agitation, filtration, mist formation. Always remember with mist formation that mists can ignite below their LEL. If you're dealing with highly insulating materials like hexane, for instance, I've seen PTFE lined vessels looked as though a machine gun has peppered them with black holes after the product is discharged to the earth of the pipe through. And again, you have to find ways of trying to stop this charge generation occurring. Mists and dust clouds. Mists, aerosol, and dust clouds can be highly charged, even when you're using conducting materials. Always remember that mists can ignite below the LEL of the liquid. They don't know how low they can go, but believe me, they can ignite below the LEL. There's not a lot known about mists and sprays, so treat them with care. Charge levels depend on how the mist is generated. It may induce charge on isolated conductors, such as the spray head itself. So make sure everything is earthed in the vicinity. So hazard summary. Establish that a flammable atmosphere is or can be present. What is the ignition sensitivity of the flammable atmosphere, the MIE? If the MIE is 25 millijoules, then you don't need to worry about brush discharges, for instance. You only need to consider cone, propagating brush, and spark. Do operational conditions affect the MIE? Higher temperatures or higher pressures, for instance, lower pressure, increased oxygen levels. Is the product insulating or conducting? So liquid conductivity will tell you whether the liquid is insulating or conducting, and the powder volume resistivity will tell you whether a powder is insulating, antistatic, or conducting. You can combine that with charge relaxation time. If you want to also look to see how charge can occur, You might like to do the chargeability study, where pouring material down a pipe you can find out how much charge is generated, which is the best type of transfer medium. Years ago, I looked at a product, a pharmaceutical product, which was going through a stainless steel plant. They were getting terrific problems, sticking, separation. So they asked us to look at it. We looked at it and found it was insulating. We also discovered the MIE was very low. And we also knew the charge relaxation time was very high. So we did the chargeability test, and we found out that going through a PVC pipe, we got very little charge. Going through a polypropylene pipe, we found very little charge. Going through a glass pipe, very little charge. Going through a stainless steel pipe, large amounts of charge. They ended up having to make a glass production plant, which was very expensive. Where will maximum charging occur within the system? So you need to look at the system that you've got and see the different parts of the manufacturing process, find out where the maximum charging can occur. Can you measure the charge rate of the plant? What type of discharges are relevant? Could you have the possibility of spark discharges, brush discharges, or even propagating brush discharges? Can the maximum stored energy be calculated? Is action needed to prevent, reduce, and control electrostatic hazards? A good instance of this, I looked at a plant and told him he was getting electrostatic sparks across a transfer pipe. He then decided to make sure it was earthed by wrapping copper foil over the full length of the transfer pipe, which went across a walkway. Yes, that seemed good in the face of it, when all I did was ask him to insulate the copper coil going through, the metal coil going through at either end. In fact, what he did was produce an electrolytic capacitor. They got a propagating brush discharge, which blew the equipment up. Again, a little bit of knowledge is a dangerous thing. So control measures, electrostatic hazards, bonding, grounding, bonding and grounding. Check to ensure there's no isolated conductors. Avoid or minimize charge generation. Prevent charge accumulation. Remove charge before hazardous potentials are reached. If avoidance of static charging and incentive discharge cannot be prevented, then flammable atmospheres must be avoided or controlled. You may need to use nitrogen, take away the oxygen. So, we talked about bonding and grounding. Bonding is the act of connecting objects together to ensure they are at the same voltage. Bonding, therefore, distributes the electrostatic charge equally between the bonded objects, so there is no risk of sparking between them. Grounding, connection to a suitable earth point with a suitable electric cable. On many occasions, I've looked at these grounding cables and found them to be broken, in bad state of repair. If you've got a electrical maintenance program, make sure you include these electrical cables into the system so they look at the grounding when they do the electrical checks. Bonding, that does not remove the risk of static sparks entirely. If an object at a lower voltage, i.e. a grounded hose, comes into contact with the equipment, this could result in a static spark discharge. The best system is bonding and grounding, if you can do this. Earthing requirements. For metal to metal contact, you should get less than 10 ohms. This also complies with lightning requirements. So you need to measure the complete pipework systems and storage systems and operating systems that you're working with, and make sure that all metal plant has a resistance of less than 10 ohms. This includes across flanges. If you find the flange produces greater than 10 ohms, then you may need to put in a bonding strap. So pipelines, usually earthed by connection to plant, flange bolts, vessels, and structure. Bonding across joints are not necessary in many cases. You can measure it and you can find out whether you've got continuity across it. If you haven't, there's a couple of reasons. So one of them may be paint. If this is the case, use serrated washers to cut into the paint and make the bond correct. Exceptions may be found, for example, sleeve couplings in some aggressive environments. So in these instances, you may want to put straps across to ensure in all cases that you have earth continuity. And that is the word you need to look at, continuity. It's no good just checking a part of the pipeline. You need to check from the start to the finish that the whole system is continuously earthed. So, movable equipment, drums, truck feeders, drum pumps, movable plant and hazardous area. Normally earthed by contact with a suitable floor, but beware of insulating skids, insulating feet or insulating wheels. If floor resistance is variable and uncertain, then use a flying lead and use an electrostatic approved clip, not just any old clip. The clip has got to be strong, powerful, and cut through any paint or inconvenience there to give a good connection. The lead is hardwired at one end. Connection has to be made before you start the operation, such as pouring out of a drum, and the connection is broken only after the operation has been completed. Again, these, as I said before, these need to be included in your electrical maintenance checks. A grounding proving unit. Again, these are quite simple. You connect them up. What they do is measure the conduction between, say, the tanker and earth and give you a red light or a green light situation. These are normally, detection system is normally in a non-hazardous area. So if you get a green light, you're okay to go on the interlock. If you've got a red light, then you've got to check it out. Something's wrong. So on a centrifuge here, you've got a braided hose. If this isn't earthed, it'll become an isolated conductor. Worse still, it may be against a plastic pipe and could result in a propagating brush discharge. So check out you haven't got that scenario. If it's metal pipe work and the braided hose is covering it to protect it, then make sure the braided hose is earthed. Again, we're down to continuity. Make sure the whole system is continuously earthed. For personnel, flying leads can be used to ground personnel, but these are impractical for people who have to move about. You'll see these on the electronics benches where you're working, and this is quite common there, where you're not moving around an awful lot. But in most industrial plants, it's not a possibility. It's most common to use static dissipative flooring and shoes. If you've got insulating floors, then you can use static dissipative mats, but make sure these are earthed. And you need to get your shoes tested properly. Don't just believe the manufacturer. Get them tested every now and again to check you are getting static dissipative shoes. The flooring as well needs to be checked to see if the surface and the volume resistivities are low and they're static dissipative. Too many times people put polishes on floors. The polishes are insulating and your floor is ruined from the point of static discharge. Total resistance between the body and earth should be less than 100 megohms. So control of static control measures use electrically grounded conductive plant, increase liquid conductivity, control flow velocities, keep flow levels low, less than 1 meter per second, prevent free falling or splashing of liquids. In other words, fill the vessel from underneath on a bent tube. Full bore valves are also important to reduce turbulence. So try to use full bore valves that don't end up causing restriction and turbulence on the system. Control of electrostatic discharges. Based on the properties and test results, if the electrostatic charges on the powder particle is sufficient to cause discharges for the surface of the bulk powder, one or both of the following measures should be followed. So you may decide to install inert gas blanketing. This was what I told you about the incident that I looked at, and that's what they chose to do. If you are going to use nitrogen blanketing, then make sure the people are using the equipment have been trained in the use of nitrogen and understanding the risks associated with inerted vessels. We attended an incident a few years ago where they used inerting and the vessel lid was opened for maintenance, but it hadn't been purged and nitrogen was still in the vessel. The maintenance guy looked into the vessel, breathed in, and fell into the vessel. Straight after that, his maintenance guy was looking for his mate, did exactly the same thing. Therefore, 2 people died because the company hadn't trained people in the use of inerting agents such as nitrogen, which is colorless, odorless. So be careful if you are going to use it. Installation of explosion protection may be your next option. So in that case, you may use explosion vents or suppression systems to ensure the safety of the vessel. Quick talk now about FIBCs and their hazards. Type A is a polypropylene insulating one. Type B is insulating polypropylene, but it has a breakdown voltage of less than 4 kV, so won't produce a static discharge capable of igniting the material. Type C, conducting threads or fully conducting. These must be earthed. How many times have I seen these be used and they think because they're type C, they're conducting. You must put an earth clamp on them and make sure the earth clamp is properly earthed. Type D, static dissipative design, worked if earthed or not. So type A, you can get brush, cone, spark, propagating brush. Do not use these in hazardous areas. Type B, they can be used, and you can use cone discharges, and you can use types B, C, and D, but they cannot be earthed. Type C, as I said before, must be earthed in hazardous areas, and type D don't need being earthed. Most expensive, but they do work. So, bulk powder product, less than 0.1 millimeter in particle size, MIE greater than 1,000. You can use in non-explosive atmospheres A, B, C, D, explosive dust, B, C, D, flammable gas or vapor, 2A or 2B, C or D. That's in 1,000 to MIE greater than 3 millijoules. If the surrounding atmosphere is non-explosive, you can use B, C, and D. Explosive dust, B, C, and D. Flammable gases and vapors, only C and D. And if the MIE is less than 3 millijoules, similar to a gas and vapor, then only C and D for any of the options you've got. So, summary of electrostatic webinar, the need for test data to understand if there is an electrostatic hazard. How do you know you've got an electrostatic hazard if you don't know if your product is conducting, insulating? The data can include the minimum ignition energy, minimum explosive concentration of resistivity, charge relaxation time, and can do chargeability for powders. MIE, flash point, lower explosion limit, upper explosion limit, conductivity for liquids. We talked about an explanation of electrostatics. What happens when you get charge generation and accumulation, for instance? What is the difference between electrical and electrostatics? Examples of incidents and types of equipment where electrostatic incidents can occur. Use this information for your plan. Looking at electrostatic hazard assessments. When you do an ATEX assessment, you should identify whether you need this as a separate electrostatic hazard assessment. Our engineers, when they come on site, will look at the products, they will look at the processes and decide whether you need this or not. And then you can choose to take it or whether you don't. You can look at charge generation and charge accumulation. We've looked at types of electrostatic discharge. We've looked at electrostatic hazards on plant, grounding and earthing, the differences between them, and how's the best way to do it, and the use and selection of FIBCs. Well, I hope you found the webinar useful and that you can take some information away with you. As I said to you, a little bit of knowledge is a dangerous thing. So if you want us to help you, please get in contact with us. Thank you for attending.